Good evening. I am Seungbin Kwon from the QISCA Journal Club team, and I'm responsible for today's Journal Club. Let me introduce you our introductory seminar presenter, Kunho Jang. Kunho is a high school student at Dulwich College, Seoul, and has interest in quantum optimal control theory. Today, he'll present us about quantum control methods for cat code encoding pulses, GRAPE and RL. The paper he used is Encoding of Qubit States in Resonators with Cat Codes by Johan Winther and Model-Free Quantum Control with Reinforcement Learning by VV Sivak and others. Then let's welcome Kunho to the stage.
Hi everyone. Can you hear me?
Yeah, I can hear you loud and clear.
Thank you. So, hi everyone. Thank you for the introduction. I'm Kunho Jang, and I'm excited to present about quantum control for cat code encoding. And the two main methods I will introduce are GRAPE and reinforcement learning. So here's an outline of my presentation. I will first discuss quantum error correction and a type of quantum error correcting code, which is cat code. And I will introduce why quantum optimal control is needed and two main quantum optimal control algorithms. And one is a traditional numerical optimization method called gradient ascent pulse engineering algorithm. And the second is a type of machine learning technique called deep reinforcement learning. So as you would know, quantum computers are quantum technologies that leverage quantum phenomena like superposition and entanglement. And it has many applications in fields from drug discovery to cryptography. And it is a very revolutionary technology. However, there's a main challenge in the current NISQ era, which is that quantum computers are susceptible to noise since it always interacts with its environment and it can't be isolated. So the area of study that strives to overcome that challenge I mentioned is quantum error correction. And quantum error correction protects quantum information, which is very fragile, and it allows for longer coherence times and more reliable computation and scalable computers. Cat code is a type of quantum error correcting code, which is used in bosonic modes such as microwave resonator, and it is very promising candidate for a successful quantum error correcting code because it is very efficient hardware-wise, since unlike traditional quantum error correcting codes like Shor's code, where quantum information is protected from noise by spreading the information. In other words, it encodes quantum information into one logical qubit into many physical qubits, it would require high overhead. But for cat code, it utilizes the infinite energy levels of a quantum harmonic oscillator, whether it's a photon or atom, and it uses infinite energy levels as infinite Hilbert space, infinite dimensional Hilbert space to store quantum information. And it encodes quantum information to cat states, which are macroscopically distinct opposite phase superpositions of coherent states. And the logical basis states I've used in the research are shown in the presentation. And it is also inherently robust to dominant error channels like single photon loss and dephasing errors. However, despite the quantum error correcting code, there's still a challenge that it requires high fidelity preparation of the cat states in order to implement the quantum error correcting code. So this is where quantum optimal control comes in. Quantum optimal control is a study where it designs external fields, for example, electromagnetic fields, like microwave pulses, to precisely steer quantum systems. And it is used to achieve high fidelity state preparation or unitary operations. And how we measure a certain quantum optimal control algorithm to be successful is by the fidelity. And fidelity is defined as a measure of overlap between the target state and the final state. So it's basically how well the state is prepared. And our algorithm would use fidelity as its performance function, or it is used as a cost function, where it's used as 1 minus f, which is set in fidelity. So more into GRAPE algorithm. GRAPE algorithm is one of the most popular numerical optimization methods used in quantum optimal control. And it basically uses Schrodinger's equation, which governs how a state vector psi evolves over time in an isolated closed quantum system with a time-dependent Hamiltonian. But a real quantum system is not perfectly isolated, so this evolution is just ideal and it's not realistic. The graph shown, the image shown in the on the right is how GRAPE works. So it's a representation of how control amplitudes consisting of n steps, each with duration dt, t over n, where t is a total time. And during each step, the amplitude is constant, and the arrow shows whether the gradient or decrease depending on whether it reaches higher fidelity or not. And the equation for fidelity is shown above, and d is the dimensions of the unitary operations. However, GRAPE is susceptible to model bias since it's a model-based algorithm. So if either the Hamiltonian that models the system is imperfect or not precise, or if you can't model all the noise using the collapse operators, it would not be completely precise and it would actually decrease the fidelity. So what I've done in my research is that I use 6 representative state transfers for cat code, and the resonator always starts with the vacuum state and it ends on a target state, while the ancilla qubit is starting on an initial state and it ends at a ground state. And they're coupled using James-Cummings coupling. So the total Hamiltonian of the system consists of the drift Hamiltonian and the control Hamiltonian. The drift Hamiltonian is the total intrinsic energy of the system. And in the equation, you can see the first term is a resonator term, and then the second term is a qubit term, and the last one is a coupling term. A and B are lowering and raising operators, respectively. And the self-Kerr terms shows an anharmonicity. And the drift Hamiltonian was converted into rotating frame from lab frame, which means it's a unitary operation where the fast oscillating bare frequencies of the resonator and qubit are removed so that larger time steps can be used in the GRAPE algorithm to reduce overhead and computational costs. For control Hamiltonian, the U1, U2, U3, U4 are the control amplitudes for adjusting using the GRAPE algorithm. And the simulated system is a coupled superconducting qubit resonator system, which is weakly anharmonic, as mentioned before. And since it's anharmonic, the transition frequencies between the energy levels are different. And the resonator was truncated to 12 dimensions, and then ancilla qubit is a 2-level transmont superconducting qubit, which was truncated at third dimension to model the leakage. And the image below shows a physical model of the qubit resonator system. So the methodology I used was Python coding, which was simulating the system through a Python library called Qtip. And On the right-hand side, it shows the parameters I've used. I tried to emulate the realistic system as much as possible by referring to other research papers and realistic constraints. And I used the initial guess pulse as Blackman pulse because it has a Gaussian shape and it's approximately equal to the Gaussian pulse, but it ensures amplitude constraints as it goes to 0 at either ends. And I made the pulse randomized by scaling it from 0.9, random real number from 0.95 to 1.05 so that it explores the solution landscape better and to prevent falling into local maximum. And I ran each state transfer 12 times so that it's able to remove all the local maxima and it also explores the solution landscape. And the convergence criteria are shown below, and then they're used to improve fidelity without reaching excessively high computational cost, since I ran it on my laptop. And here are the results. First, I ran it in a closed system using the Schrodinger's equation, and the plot on the right shows the 4 control amplitudes for the 6 representative state transfers. And on the left-hand side, there's fidelity, and the fidelity was very high for all 6 state transfers since it was an ideal closed system where there's no noise. And then I used, after the GRAPE algorithm was completed, the control pulses with best fidelities in each of the 6 state transfers were reevaluated in an open system to consider the noise in a realistic system. And an open system is governed by Lindblad master equation, which is an ordinary differential equation, which governs the stochastic open quantum systems. And it uses density matrix formalism, unlike the state vectors. And the collapse operators are mathematical. It's the way I mathematically modeled 3 different types of noise channels, which are single photon loss, amplitude damping noise, and qubit dephasing error. And on the right-hand side, the results are shown. The fidelity decreased from the previous closed system. However, it is still sufficiently high since they all exceed 99.4%. And the Wigner function plots show the probability distribution of each state, and the lobe and interference patterns show superposition of the cat states. However, as mentioned before, GRAPE has a limitation since it's a model-based algorithm, and model-based algorithm requires specific and precise Hamiltonians and collapse operators which model the system. But in reality, in an experiment, the quantum hardware might be not perfect, or there might be unmodeled dynamics since I can't account for every single noise channels. So the way I attempted this issue is through an alternative model, which is deep reinforcement learning. And it sufficiently solves this issue since it's a model-free algorithm. So more about the deep reinforcement learning. Deep reinforcement learning is an agent that learns to make decisions by interacting with the environment to maximize cumulative reward. And it learns by trial and error, so it doesn't depend on the model. And it instead learns from the experimental feedback, which is the reward. And it consists of an agent, which is the learner and the decision maker. And more specifically, I'm planning to use proximal policy optimization agent, in short, PPO. And the environment is the system that the agent interacts with. And in this case, it will be the open quantum system versus a qubit resonator system as introduced before, and the state is the environment at a given time t, and it can just be the quantum state psi. Action would be something the agent does to influence the environment, and it would be the control pulse applied. And finally, the reward is a feedback signal, and in this case, it's fidelity. So the agent and environment's interaction can be mathematically described by Markov decision processes, and it has an important property where the current state and reward only depends on the state and reward immediately before, and this means the current state and reward completely describes the environment without any past states. And the dynamics function is probability of moving from current state to the next state and receiving a particular reward R, given that this action is A. And the agent environment interaction is visualized in the image below. So there are many types of reinforcement learning agents. It can be largely divided into two, model-based and model-free. As I mentioned before, PPO agent is model-free, and there can also be model-based reinforcement learning agents. And it can also be divided into two other ways, which is on policy and off policy. So this basically means for on policy, it only uses the current policy, and all the old policies after the policy update are deleted. While off policy reuses the past experiences and policies as it can store them, which makes it more sample efficient. Some examples include PPO and reinforce for on policy, and soft actor critic and deep Q network for off policy. So here are some more technical terminologies for reinforcement learning. The trajectory is a sequence of states, action, rewards, and the next state. So it can be presented as a quadruple state, action, reinforcement, reward, and next state. And trajectories provide data from which the agent learns and updates its policy. So talking about policy, the policy is represented by the symbol pi, and it's the agent's behavior or strategy that maps states to actions. And it represented as the probability distribution parameterized by using function approximator like deep neural networks, like pi sub theta. And theta refers to the collection of all learnable parameters that define the deep neural network, responsible for generating the policy. Theta also represents all the weights and biases within this deep neural network. When we train the PPO agent, we're essentially adjusting and optimizing these weights and biases each time to achieve the highest reward, which would be the fidelity. And the policy updates can be shown in the equation. So the formula basically means that the next theta, it wants to return the maximum expectation value of the reward. So here's more about proximal policy optimization, PPO, which is the agent I'm planning to use. And it's a type of actor-critic algorithm structure. So in other reinforcement learning algorithm, there's actor policy pi, which picks the actions, and it can operate like that, but it adds a critic in PPO agent where the value function evaluates and helps improve the decision making so that the actor is not making stupid choices. And the policy update can be modeled by the equation shown below, which is similar to the equation I've shown in the previous slide. And the most important function in PPO agent is the clipped objective function, which is what makes the PPO agent so stable. And it's the reason why I chose PPO over other agents. So the complicated looking formula basically means, so the epsilon in the formula is basically the maximum allowed deviation from the new policy from the old policy. So the ratio between the old policy and the new policy is multiplied by the weights advantage function. And then if the ratio is greater than 1 plus epsilon, it is capped, so it is limited at that. So it returns 1 plus epsilon, and it's the same for 1 minus epsilon. If the ratio is below 1 minus epsilon, it returns 1 minus epsilon, and it returns the ratio only if it lies in the range between 1 minus epsilon and 1 plus epsilon. So this basically prevents the PPO agent from making a big jump in policy updates. So it only allows small changes so that it is safe. The advantage function, which is used in the objective function, it estimates how much better an action A is than an average action given state S according to old policy. Capital R is the immediate reward, and the gamma is the discount factor, which is between 0 and 1. If it's closer to 0, the RL algorithm can be described as myopic, which means it focuses on the immediate rewards. And if it's closer to 1, it's more far-sighted, so it focuses on long-term rewards. And the training process is not that complicated. So it's basically structured into epochs, and the agent collects a batch of experience episodes within each epoch. And the policy doesn't update until each epoch is finished. And the policy update is basically a gradient ascent step, which is kind of similar to the GRAPE algorithm since they're both gradient based, and the alpha in the equation is the learning rate, which determines the next theta. And the image below shows how the deep neural network doesn't learn directly from the environments of the superconducting system, but it goes through a series of computers, then it receives information through the form of reward. So here are some advantages of PPO agents. The second one, adaptability, is more about the general reinforcement learning algorithms. Since it's model-free, it can adjust to other systems and it can account for unmodeled dynamics since it doesn't use the Hamiltonian, and it instead uses the experimental feedback, which is a reward. It also prevents performance collapses. So when reinforcement learning was first introduced, the agent was deep Q network, and then also, although it was successful in some cases, sometimes the policy update made drastic changes, so it led to sudden drops. So PPO agent was made to prevent the sudden drops so that it's more stable. And the high stability allows it to handle stochastic environment like open quantum system. And the main limitation of PPO agent is sample efficiency. So as mentioned before in the types of RL agents, reducing the number of experiments, it requires to reduce the number of experiments needed for convergence, since it doesn't reuse the past policies and it just discards them after every policy update. So one way to solve this is through pre-training, which I saw in a research paper. It used pre-trained data from GRAPE algorithm, and then it used it to train the PPO agent so that the computational cost is lower. And what I will do in the future is I will code the PPO agent since I've learned the theoretical framework, and I will compare it with GRAPE, the fidelities, and I'm currently in the process of doing that. And I might combine it with GRAPE as mentioned before, so that it can be pre-trained and the computational costs can be lowered. Also, there are some reinforcement learning algorithms which reduces the frequency of rewards and is sometimes more effective. So I could experiment with that. And reinforcement learning algorithms are easily adaptable to different systems and states. So I don't have to stick to the catch states. To conclude, in this presentation, I've explored two main algorithms. One is GRAPE and one is PPO. And for GRAPE, I've conducted the research and I achieved high fidelity both in closed and open quantum system. But since it's a model-based algorithm, I chose to find an alternative solution, which was the PPO reinforcement learning agent. And then since it is not affected by model bias, it is more applicable to real-world experiments, and it's very stable due to the clipped objective functions. And I think both methods will significantly contribute to achieve fault tolerance for cat codes. Thank you for listening to my presentation. I'm very grateful for this opportunity.